Hello and welcome to the second part of the 21st lecture of CS2100. So in this second part, we are going to introduce trees, which are special kinds of graphs. In particular, if you look at the outline of this part 2, we're going to introduce trees, we'll show what they are, and then we'll do some proofs about trees. We introduce the concept of spanning trees and minimal spanning trees, and we'll give algorithms for how to compute those. So let's get started. So a tree is a connected simple graph that has no cycles. And then a leaf is a vertex in a tree with degree 1. So here on the left, you can see an example of a tree. And on the right is an example of a graph that is not a tree, because the graph is not connected. Another example of a graph that is not a tree would be this, because it has a cycle. Okay, so clearly trees are used a lot in computer science and programming. Some of you maybe have already seen algorithms that use trees. So they're very important data structure in computer science. So let's do a simple proof about trees. So the proposition we want to prove is that for every tree G, removing any edge from G will result in a disconnected graph. Okay, if we think about a couple of examples, it kind of makes sense, but we'll have to prove it as well. So this is an example tree. And let's say we remove this edge here. Clearly, we're going to end up in a disconnected graph. In fact, any edge that I remove in this tree, I'm going to end up in a disconnected graph. So the intuition tells us this is right, but let's now try to prove it. So let's rewrite this proposition slightly. So if G is a tree, then removing any edge from G results in a disconnected graph. Or we'll do the proof using proof by contrapositive. So the contrapositive of this proposition is if removing any edge from a simple graph G results in a subgraph that is still connected, then G has a cycle. So the negation of G is a tree is G has a cycle. Okay, so let's see now how we will prove that. So let an edge AB in G be given such that removing it results in a connected subgraph G prime. Since G prime is connected, there is a walk from A to B, where A and B are two vertices. For example, we have this walk A, A1, A2, A and B. So since G prime is a subgraph of G, this walk is also in G. Adding the edge AB to this walk forms a cycle. So we'll get a cycle that goes from A to A through B. Since we've proven this contrapositive statement now, that G has a cycle, and this contrapositive is logically equivalent to the original statement, we prove the original statement as well. And that concludes our proof. And here is the complete structure for you to review. Okay, so we've done a lot of induction proofs when we were covering section 2 or 3 in our books. So induction is an important strategy for doing proofs that comes up over and over again, especially when doing proofs in graphs and trees, because they have a natural inductive structure to them. So let's try to prove the following proposition using induction. For every tree G with at least one edge, G has at least two leaves. We'll rely on the proposition 4 that we already proved. For every connected graph G with at least one edge, if G has no cycles, then G has at least one vertex of degree 1. Okay, so as a quick reminder of the structure of the induction proof, so we have a problem statement, then we have to identify base case, and then we have to write down our inductive hypothesis. Finally, we're going to do an inductive step in which we're going to leverage the inductive hypothesis to prove it. So let's see how that would look like in this case. So our problem statement, Pn, says that every tree with n edges has at least 2 leaves. Okay, our base case for the value 1 is that the tree with only one edge has 2 leaves. That's obvious. We can even draw it like this. Our inductive hypothesis is let m greater than or equal to be given such that p2 to pm1 m minus 1 have already been checked. And then our inductive step, we're going to prove that pm holds by relying on this inductive hypothesis. So let the tree G with m edges be given. There is then a vertex V with the degree 1, and that follows from proposition 4. Because of that, only one edge V, W in G has V as an endpoint. So then we can form a subgraph G prime by removing vertex V and edge VW from G. Now G prime is a tree with m minus 1 edges. By the inductive hypothesis statement, P of m minus 1, G prime has at least 2 leaves. Vertex W is the only one in G that has a different degree than it does in G. So we can choose one of the leaves G prime, but not W, and call it U. Vertex U has the same degree in G prime as it does in G. Hence, U and V are leaves in G. And therefore, by induction, we found P of n to be true. And that concludes our proof. So spend some time trying to understand this proof in more detail. Go through the structure and make sure it really sinks in. Okay, let's now introduce spanning trees. So let G be a simple connected graph. The subgraph T is a spanning tree of G if T is a tree, and every vertex in G is a vertex in T. So here is an example. So on the left, we have graph G, and on the right, we have an example of its spanning tree. So as you can see, spanning tree contains all the vertices that G contains as well, but it is a tree. So that's one example of a spanning tree. Okay. So what is an algorithm to compute spanning tree? So we begin with a simple connected graph G0. And then for each I greater than or equal to 1, as long as there is a cycle in G I minus 1, we choose an edge E in any cycle of G I minus 1 and form the subgraph Gi of G I minus 1 by deleting this edge from G I minus 1. And once there is no more cycles, the final result Gk is a spanning tree of the initial graph G0. So it's a very simple algorithm to understand and implement, and it will lead to a spanning tree being generated. Note that there is some non-determinism here in choosing which edge we're removing from the cycle. So it basically doesn't matter which edge you remove from the cycle, it will always lead to a spanning tree in the end. So here is an example. We removed an edge, we removed another edge, There is another cycle, this triangle IFH, so remove an edge. There is another cycle comprised of vertices I, E, H. We're going to remove another edge. There is another cycle comprising of vertices I, E, F. We remove another edge in this cycle, and we have another little triangle comprising of vertices A, B, D. We remove an edge, and now we have this big, large cycle that goes all the way around. And so we're going to remove one more edge, and now we don't have any more cycles, and this is a spanning tree of the initial graph. Note that if we removed edges from cycles, different edges from these cycles, we might end up with a different spanning tree. Okay, so that's the spanning. Okay, so now that we learned what spanning trees are, let's see what minimal spanning trees are. So recall that the weighted graph has a cost label on each edge. Then if G is a weighted graph, T is a minimal spanning tree of G if it is a spanning tree and no other spanning tree has smaller total weight. So here we have a really simple example graph that has weights on edges, which are these numbers. And so an example spanning tree, clearly there's a cycle here, A, B, D, C. So to form a spanning tree, we can remove our one edge. And so we remove this bottom edge. So this is a perfectly fine spanning tree of this graph, but it's not a minimal spanning tree. And the minimal spanning tree would be the one where we remove this edge with the highest weight on top. So this is a minimal spanning tree for the graph on the left. So let's look now at the algorithm we can use to compute minimal spanning tree. It's so-called Prim's algorithm, and you have it in your textbooks as well. So given a connected simple graph G with n plus 1 vertices, and that is given to us. So now let V0 be any vertex in G, and let T0, that is equal to V0, be a tree with one vertex and no edges. Now for each k from 1 to n, let the set EK be a set of edges from G, and let's label them E, where E has one endpoint in tk minus 1 and the other endpoint not in tk minus 1. And let EK be the edge in the set of edges EK with the smallest weight. And then tk is then the tree obtained by adding this edge EK along with its vertex not already in tk minus 1 to tk minus 1. And finally, when we converge, tk is going to be a minimal spanning tree of G. So here in an example problem. So we have this graph G in the bottom right, and we want to find the non-minimal spanning tree of G as well as a minimal spanning tree of G using Prim's algorithm. So let's first do a non-minimal spanning tree of G. So let me redraw this graph. Let me just select the color. So this is what we have. And what are all the connections? Actually, let me erase this one. So let me draw all the connections between them. We have this, we have this, 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 we have this and this, and we have this and this. And note that for finding a non-minimal spanning tree of G, we don't care about weights. We only care about edges and cycles. So we're going to identify cycles in this graph one by one, and whenever we identify cycle, we have to erase one of the edges in the cycle. Let me also label the nodes. I forgot to do that. So this is node C, this is node B, this is node D, there's node A and E. Sorry, I should say vertex instead of node. Okay, so keep identifying cycles and erasing an edge in the cycle. So we have this cycle CDE, and so I'm going to erase this edge. And note that you can pick cycles in whichever order you want, and you can erase whichever edge you want from a cycle. Now we have the cycle CBA, so I'm going to erase this edge. We have the cycle CDB. I'm going to erase this edge. Okay. Now we have a cycle AED, so I'm going to erase this edge. We have a cycle AEB. I'm going to erase this edge. And now we still have this big cycle going all the way around, and I'm going to erase this edge. And so this is a non-minimal spanning tree of G. Okay, now let's find a minimal spanning tree of G by applying Prim's algorithm. So what is the algorithm? So we start from a vertex, let's say C. And then we add an edge and a vertex to the graph that is connected to C with the smallest weight. So C is connected to B with 9, to A with 10, to E with 7, and to D with 8. So we are going to add E. And the weight here is 7. Okay. Now, from all the outgoing edges from these two vertices, we have to find, again, the one with smallest weight that connects us to a new vertex. So in this case, it's going to be this connection from E to A. Okay. We keep repeating this. So the next one is going to be, what is the next one? Smallest one is the connection from A to D. So we are going to connect A to D. Okay. And finally, the last edge we are going to add is the one that connects A to B. It has the weight 3, which is the smallest weight. And now we added all the vertices, and that's the minimal spanning tree of G. And so here is the solution without me drawing it. And as you can see, minimal spanning trees are the same, while spanning trees are different. And indeed, depending on how you're breaking cycles, you can easily end up with different spanning trees. Okay, so that was an example problem with the spanning trees. Let's conclude with one more proof. So we want to prove that for every connected graph G with at least one edge, if G has no cycles, then G has at least one vertex of degree 1. If we reward that proposition, we want to prove that every tree has at least one leaf. So how do we do this? Let T be a tree with n edges. And then, by our theorem 7 from the books, T has n plus 1 vertices. If each of these vertices has degree greater than 1, then the sum of the degrees of the vertices is at least 2 times n plus 1, which is equal to 2n plus 2. However, by theorem truth from your books, the sum of the degrees of the vertices is 2n. So since 2n plus 2 is greater than 2n, it is impossible for every vertex to have degree greater than 1. And T must have at least one vertex of degree 1. And this vertex is the leaf. And that concludes our proof. And this also concludes this part 2 of our lecture 21. So make sure to learn all the terminology related to graphs and trees. Learn what minimal spanning trees and so on, and make sure to understand these proofs and to practice them. Thank you, everyone.